Hello and welcome to another video. In this video, we will discuss about the Routh-Hurwitz criteria. Routh-Hurwitz criteria helps us to analyze the stability of a closed-loop system. Suppose you have a controller and a plant G of S. Now you reduce that entire system into its transfer function form, closed-loop transfer function, and the denominator of that closed-loop transfer function is called the characteristics equation. We will use this characteristics equation to analyze the stability of the closed loop system. And the Routh-Hurwitz criteria helps us to analyze the stability of this closed loop system. We will see an example for this. Suppose the characteristics equation of a simple second order system, that is a denominator of the closed loop transfer function of a simple second order system be s square plus 3s plus 2. And we will construct a Routh-Hurwitz table. Now suppose our characteristics polynomial f of s is something like this: a naught s raised to n plus a1 s raised to n minus 1 plus so and so up to a n minus 1 into s plus a n. So a naught 1 are the coefficients and these are the s terms: s raised to n, s raised to n minus 1, s, and the final constant term. And if the characteristics equation is written in such a manner as a descending order of the s powers, then we can fill up the first two rows of the characteristics polynomial as the highest degree Sn and s minus 1 as alternating terms of this coefficients. So we will start with the highest coefficient, this a naught s raised, which is the coefficient of s raised to n, will be written in the first as the first element, and then alternating terms. So a2, a4, a6, and then we will write the coefficients of s raised to n minus 1, s raised to n minus 1 as a1, a3, a5, a7. Those are the alternating terms from s raised to n minus 1. And after that, after writing the first two rows, we will then calculate all the other below rows. So s raised to n minus 2 will have terms b1, b2, b3. And how are this b1, b2, b3 calculated? b1 is calculated in the two rows which are just above this s raised to n minus 2. So from this first two rows, from this two rows, we will calculate b1. So that is nothing but a1 into a2 minus a0 into a3 divided by a1. So this element multiplied with this element minus this element multiplied with this element, and the whole divided by this element a1. Similarly, b2 will be calculated from the first column as well as the third column. So a1 multiplied with a4 minus a5. So now to calculate b2, we will use the first and the third column of the previous two rows. From that, a1 multiplied with a4 and a5 multiplied with a0 divided by this element a1. Similarly, b3 will be calculated from the first and the fourth column. a1 multiplied with a6 minus a0 multiplied with a7 divided by a1. Similarly, in the below s raised to n minus 3, we will have the elements c1, c2, c3. So c1 will be calculated from the previous two rows and considering the first and the second column. C1 will be b1 into a3 minus a1 into b2 divided by b1. Similarly, c2 will be calculated by the previous two rows considering the first and the third column. So that will be b1 into a5 minus b3 into a1 divided by b1. So that continues. So this is how we calculate, how we fill up the table. Now for this example, we have three coefficients to fill the Routh-Hurwitz table. So we will see how we will fill the table. So here the coefficient of s square is 1. So that is written here. The coefficient of s is 3. that is written here, and the constant term is 2, that is written here. So the highest element is a square term, so we'll start with a square and then alternating after the square, then we have, so that 2 elements are filled here, and then s raised to 1, 3 is the coefficient, and rest all the rows are, all the elements are 0. Now we have filled the first 2 rows. Now to calculate this element, we will use this formula. So A1, that is nothing but 3 multiplied with 2. So 3 multiplied with 2 minus 1 multiplied with 0, 1 multiplied with 0 divided by this element 3. So that is nothing but 3 into 2 divided by 3. That is nothing but 2. That is how we got this element 2. So that is how we fill up the rows. So row 1 and row 2 is filled. We have filled the other rows of the Routh column. And now we have to check the signs of the first column. Once we have filled the Routh-Hurwitz table, we need to check the signs of the first column. So since the sign is all positive, the conclusion is that since there is no sign change, all roots are in the left half of the complex plane and the system is stable. If suppose there is some sign changes, the number of roots that lie on the right half of S plane would be equal to the number of sign changes. We will see examples like that. So here there is no sign change and all the elements are positive. So we will have all the roots in the left half of the S plane. So that is the conclusion. So the system is stable. This is how we analyze the stability using the Routh-Hurwitz criterion. So we will start with the characteristics equation and then we determine whether the system is stable or not using this Routh-Hurwitz table. We have the characteristics equation s cube plus 2s square plus 3s plus 6. So we'll start the first 2 rows as s cube and s square. So s cube is the highest element here. So the coefficient of that is 1 and the alternating term. So the next coefficient is 3 and the coefficient of s square is 2 and the alternating term is 6. We are filling the first 2 rows of the Routh-Hurwitz table. Now to find the next element, we will calculate from the previous 2 rows considering the first and the second column. So 2 into 3 minus 6 into 1 divided by 2. So 2 into 3 minus 6 into 1 divided by 2. So the numerator is 0. So the entire term becomes 0 and we fill up with 0 here. So this term is not required here. And we fill up the next element. This is calculated from the previous 2 rows. 0 into 6 minus 0 divided by 0. So that doesn't make any sense. So we cannot divide a term with 0. So what we do is we replace this 0 with a small value called epsilon. So this configuration typically leads to a complex root. So the presence of the 0 shows that, the first column shows that it is a complex root and the further analysis with 0 epsilon substitution is needed. So instead of 0, we will substitute it with epsilon. So instead of 0, I'm substituting it with epsilon. Now when we calculate the next element, we get epsilon multiplied with 6 divided by epsilon, where epsilon is a very small value. So we cancel these epsilons and we get 6 value here. Now we analyze the first column of the Routh-Hurwitz table. So all terms are positive. There is no sign changes. Hence, the system is stable. But the presence of the 0 shows that there are roots on the imaginary axis on the S-plane. So this is the S-plane. There is roots in the imaginary axis. And how many roots are shown in the imaginary axis is got from this. So there is one root in the imaginary axis. And that makes a system marginally stable. So if all the roots are on the left, it is stable. If roots are on the right and on the imaginary axis, then it is marginally stable. And now we will move on to another example. So this is a fourth order system. We have s raised to 4 plus 3s raised s cube plus 3s square plus 2s plus 1. So we will fill up the first two rows of the Routh table. So since the coefficient of s raised to 4 is 1, we fill up 1, and then the alternating terms 3 and 1. So 3 and one more 1. And s cube is 3. So here we have 3 and 2. So these are the first two rows. After that, we calculate this element. So to calculate the first element of s square, we use the previous two rows. So 3 into 3 minus 2 into 1 divided by 3. So that gives you 7 by 3. And this element is 3 into 1 minus 0 into 1 divided by 3. So you will end up with 1. And after calculating s square row, we go on to calculate the s raised to 1 row, which is calculated by from the previous two rows. And 7 divided by 3 into 2 minus 3 into 1 divided by 7 by 3. So we will get 5 by 7. And the other element is 0. And to calculate s raised to 0, we use the previous two rows. And it is nothing but 5 by 7 into 1 minus 7 by 3 into 0 divided by 5 by 7, which will give you 1. Now we will check the first column. All the signs are positive, and we will conclude that there is no sign change in the first column, which indicates that all poles are in the left half of the complex plane, making it a stable system. Now we will see another example of a case of an unstable system. So here the characteristics equation is s cube plus 4s square plus 3s minus 5. So s cube has a coefficient of 1. So we have started with 1. And then alternating terms, you have 3 here. And then the coefficient of s square is 4. You have 4 here. And alternating term is minus 5. Minus 5 is here. So we have filled the first two. Now to calculate s coefficients of the rows of s raised to 1, we have 4 into 3 minus 5 into 1. So that becomes plus divided by 4. So that will be 17 by 4. And the next element is 0. And after filling up s raised to 1, we go on to fill up the s0 coefficients. So 17 by 4 multiplied with minus 5, 0 multiplied with 4 divided by 17 by 4. That will give us minus 5. So here when we check the first column of the Routh-Hurwitz table, there is a sign change. So here it is from positive to positive. Here it is from positive to positive. But from here to here, you have a positive to negative sign change. So there is a sign change in the first column indicating that at least one root is in the right half of the complex plane, which means the system is unstable. So from the calculation of the sign changes, we can note that how many roots are lying on the right half of S-plane. So when a root lies on the right half of S-plane, the system is unstable. So this is how we analyze the stability of a system. So we have seen examples of a stable system and an unstable system. Thank you.